Hello, everyone. Let's take a look at some physics pertaining to projectile motion to, let's say, a cannonball having been fired. We know the speed at which the cannonball has been fired in one instance, and we also know the range that is covered by the cannonball. At that point, I'd like to find out what angle had to have been used given the fact that we know the range and that we know the speed that the cannonball has been fired at. Well, it'd be nice to know the angle at which it was fired, and it'd be nice to know how long it took for the journey and how high it went, and that's the angle. We are under the assumption that practically always, unless it's a 45-degree angle that solves the whole matter, the only other complementary angle to the 45-degree angle is another 45-degree angle. If the initial angle that we used, we'll call it the low angle, the cannonball is not lifted at a high angle, but it still makes the journey of X. Fantastic. It makes the journey of X. How long does it take? What's the maximum height attained when it makes that journey? How long does it take? What's the maximum height that is attained? And what was the angle that was used? So I'm going to call that the low angle. It's not lifted up too high, and it's going to be theta sub L, theta sub low, time of flight, time sub low, or T sub L, and H sub L. So theta sub L, T sub L, and H sub L. We are going to work under the assumption that unless it's a 45-degree angle, because the 45-degree angle has its counterpart, which is another 45-degree angle. They're complementary, they add up to 90 degrees. The other angle that makes it work is an angle that you add to the first angle, theta sub L, and it'll add up to 90 degrees. So if it was a 10-degree angle for the low side, it wasn't lifted that high for you to fire it and make everything happen. If it was a 10-degree angle, then the other angle is going to be an 80-degree angle that'll make the same phenomenon happen. What do we mean? It'll make the same range occur of a distance of X. The 10-degree angle will make it work, and the 80-degree angle will make it work. In general, when these phenomenon are being looked at, if there's no air resistance, the low angle is something, and the high angle is the complement of the something. So it's theta sub L for the low angle, and theta sub H is 90 minus theta sub L. So if 10 degrees is the initial that'll make this journey of X occur, then if 10 degrees is the one that works, then 90 minus 10, 80 degrees, is the other angle that'll make it work. Now, what's going on here? Well, if you project everything downward, you guys, it's not a very high projection. You're not picking up the cannon too high, and you're firing this thing out. No air resistance. If you're not picking it up too high, there's a very big X component of velocity. So it's going to get to wherever it goes really fast. It has to. It doesn't have a whole lot of flight time because it doesn't get too high. If you lift the cannon to an angle that is complementary to the theta, if you lift it to an angle that is the complement of theta, if this was 10 degrees and the other one's 80 degrees, you lift it to 80 degrees, the X component's not going to be that big. But I guess this problem can get away with that because there's a lot of flight time. It has a lot of time to fly at that slow v sub x speed. So as this thing is going up, on the high side, it's going to have a lot of height, a lot of time, so it doesn't have to have a big X component of velocity. It'll still make the journey of X. For the other one, it doesn't have a lot of time, but luckily it has a big v sub x component. So they should work out and they're complementary. We'll talk about it in a little bit. But that's essentially where we're going with this, guys. You're looking at theta sub L being something, and theta sub H being 90 degrees minus that something. This is how it works in matters such as that. Given ideal circumstances, no air resistance, and the like. So, well, we're told that the maximum range, or the range that where the cannonball lands, is 5 kilometers away from where it started. And the speed initially when it's fired out, and I did this in class, you know, it depends who's watching this and what class you're in or whatever, but we just saw this very shortly before I'm making this video. We saw that, you know, that 1 kilometer per second, man, it's really going to get to where it's going to go really fast, so I don't need a big angle. The other one, I'm going to need a real big angle. Theta sub L is going to be really small, but theta sub H is going to be 90 minus really small, which is going to be really big. It's not going to be a 90-degree angle, guys. You never fire anything up into the air that's potentially dangerous, like a cannonball. You never fire something like that up into the air at a 90-degree angle, because where it started is where it'll end. If you don't believe me, I mean, come over here, put 90 degrees right here, and it spits it out accidentally in a sense, or just pretty much consistent with the mathematics. 2 times 90 is 180 degrees. 2 times 90 degrees, 180 degrees, the sine of 180 is 0x. There is no range. Where you fired it, it lands right there. The joke we always make is, well, make sure you're running away from that cannonball because it's coming right down, right? So you got to watch that, I mean, in a sense. So we know a good amount, and we, like I said, those with whom I've spoken about this, who are in my classes and meet me in person or have looked other places in my notes, have seen this, and we can see it here as well. Let's see how this whole thing plays out. Well, to solve all this, guys, we got to use, you know, a lot of bread and butter stuff. We got to use this. We got to use this. We got to use this, and we're going to be just fine. They're telling us that V is 1 kilometer per second. That's 1,000 meters per second. Those who were with me when I did this realized I was a little apprehensive about going that big with this thing. We'll maybe put something smaller later on and kind of see that the numbers are going to be different. 5 kilometers is 5,000 meters. So what we have here is 5,000 meters. 5,000 meters is the range that it'll go to, and 1,000 meters per second is the muzzle velocity coming out of the cannon. We got T equals 2V sine theta over G, H equals V squared sine squared theta over 2G, and X is V squared over G times the sine of 2 theta. And we've done all that already in class with together. Again, who's watching, whoever's watching the video. At some point or another, you've seen these equations. People in my classes face-to-face have definitely seen these equations already, quite a bit. If you've got a right triangle, and C is the hypotenuse, and A and B are legs, C squared equals A squared plus B squared. The sine of theta is the opposite over the hypotenuse, A over C. The cosine of theta is the adjacent over the hypotenuse, that's B over C. The tangent of theta is the rise over the run. It's the opposite over the adjacent. That's A over B. The inverse sine of any real number, and for our purposes, the inverse sine for any real number, but let me just kind of make it a little more palatable, I think. The inverse sine of some number, which can be written as a ratio of something, the inverse sine of something, you're finding from what angle you found a ratio of A over C. Well, A over C came from the angle theta. So the inverse sine of A over C is the inverse sine of, well, A over C, we said, is the sine of theta. The inverse sine of the sine of theta, in a sense, they annihilate each other, and you got theta. Cosine inverse of B over C is from what angle do you get a B over C ratio? Well, wait a minute. B over C occurs in the same triangle as A over C occurs. And it occurs in the same triangle as A over B occurs. They all occur in a triangle that's got theta as the angle under consideration. So the inverse cosine of B over C is the inverse cosine of cosine theta. It's the same theta. They all belong to the same triangle, and this is the same angle that's associated with A, B, and C. The inverse tangent of A over B is the inverse tangent of the tangent of theta. Tangent of theta is A over B. That's theta. Basically, they don't really tell you the real numbers that are being put in there. Hey, pretend this thing is a ratio. But any real number they put inside of the argument is between the parentheses here. Between the parentheses here is this thing called the argument. Anything they put between those parentheses is a ratio of two sides. And that can be, even if it's a negative number, it's kind of a unit triangle that's really occurring. You could draw a triangle here, a unit triangle also on a unit circle. It's something like this. We don't want to go into this, we don't need to go into this greatly at this level for the non-calc version of the course. But if you got something like this, and you got this, and there's your C, or it's an R, or whatever it is, and this is a theta, and this right here is B, and this right here is A, you know, this thing could get flipped over this way, in which case that B would be a negative number. It wouldn't be positive B, it'd be a negative B. This thing down here would be a negative A, and this would still be C, because that's the length of this thing. You know, what does that mean? Well, angles can go on into infinity. If I keep spinning this thing around counterclockwise, I get big positive numbers. This thing spins around 500 times from where it is here, it'll come right back here. That's a pretty big angle. Well, yeah, if you put that big angle in your calculator, it'll spit out the answer as though this guy was just rotated, not even rotated, got up to here. Now, if you take it from here and go 500 full turns to get back here after 500, the tangent, the cosine, the sine are the same as it was just with the theta. But if you rotate it 360 degrees 500 times, you got theta plus 500 times 360, whatever that is. You know, at the end of the day on something like that. So you're looking at it, let me kind of look at it myself here right now, just kind of look at it. That'd be 1800, 18,000 would be 180,000 degrees, 180,000 degrees plus theta. Well, that's just 500 rotations. You're going to get the same answer. If the sine of theta here was 0.5, theta plus 180,000 degrees is also going to be 0.5. So that's a little, you know, for some of the calc version of this stuff, something to keep in mind. I'm not going to emphasize that greatly. The big thing is, you know, come up here and see how this all plays out. Now, I've already done this. I've already done some of this some time ago. Not a tremendous amount of it, but I definitely have done some of this some time ago. The inverse sine, and the inverse sine does not mean, the inverse sine does not mean 1 over sine. It's just a symbol meaning find me the angle from which that ratio came. Inverse cosine is not 1 over cosine. It is the value of theta that would give me this value of the cosine. The inverse tangent is not 1 over tangent. It is find me the angle that gives you the ratio. Find me the angle that possesses theta. Well, A over B came from theta. A over C came from theta. B over C came from theta. Sine theta, cosine theta, and tangent theta all came from that triangle. So if I get the inverse of A over C, find the angle from which A over C came. If I get the inverse of B over C, find the angle. If I get the inverse, if I get the inverse sine of opposite over hypotenuse, the inverse sine of A over C, that's theta. This came from theta. If it's another angle, it's going to be a different ratio. The particular ratio, A over C, the inverse sine of A over C is going to be theta. The inverse cosine of B over C is going to be theta. The inverse tangent of B over C is going to be theta. And these are not 1 over cosine, 1 over tangent, 1 over sine. They're just find me the theta. Find me the theta from which these ratios arose. Now, I said that for those of you that were in my class very, very recently, because this is very recently after I discussed this. I already said that, okay? And some time ago I said this too. at least sometime before any of this was said, I said this. Now all of that's in front of you. You have to have a decent basic knowledge of algebra and trigonometry to get through even the non-calculus version of classes like this, where it's just basic Newtonian mechanics, and there's a lot of algebra involved and a lot of trigonometry involved. To get through classes like that, you have to have a strong basis in algebra and a strong basis in trigonometry. Trigonometry is a pretty complicated site. I'm not talking about some kind of graduate level study of trigonometry and some graduate level study of algebra, but you have to have a strong basic knowledge of algebra, and you have to have a strong basic knowledge of trigonometry to get through classes like this. So I've already shown this. You got to look at it on your own a little bit, see the tutors, everything else, but you got to be on top of this, guys. You got to know this. Today in the class, in the class where I discussed this, I did do a lot of trigonometry to the extent that I kind of stopped doing some stuff that I had planned to do, but I think it was a good idea to do that because I at least wanted to have that all put down on the table for you before the first exam happens. Before the first exam happens, I want you to be on top of this stuff. Some people felt pretty comfortable with this already. Some did not, I could tell. So I decided to just kind of take a little time on that. So because I took some time on that, I want to just take some time and do this problem if I had more time. Obviously, it's a little easier to do this stuff in a class if you have an hour and a half or an hour and 15 minutes to do it rather than 50 minutes. An hour, if you have 75 minutes, you tend to have a unified approach for a long time, and that's a good way to go. We don't have that. We only meet for 50 minutes at a time if you are in one of my classes that meets 3 days a week. If you're one of my classes that meets 2 days a week, the 75 minutes per time has its merits. It really does. Okay, so that having been said, we have derived these already, and let's just try to get some answers to what the heck is going on here, guys. Now, obviously, I do have to erase this stuff. You do have the feature on, you do have the technology in the film. You just go back and just look at everything I'm doing while I'm erasing what I got to erase. So let me try to think what I'm going to put here, what I'm not going to put here. Let's start with this. The numbers got a little on the crazy side. It kind of went a little bit against our intuition, but I can maybe cut this thing in half, the 1,000 meters per second, and see how that whole process proceeds. Okay. There is a lot here. Ideally, guys, I don't like erasing any of this stuff, but you've got the feature where you can go back and look at what's on there as well. So let me kind of see a few things that we could say here, guys, and we'll kind of take it from there. Okay, we wrote this stuff. You're going to see it again in bits and pieces. Here I'm just initially presenting it to you. We know about all the symmetry associated with motion. Let's see what we got. Well, okay, I'm looking at the low end of this thing. I'm thinking, okay, you're going to project this thing at a small angle, at a low angle. Wow, well, nobody get too close to it because this thing's coming at a low angle, and let's see what it does. That's going to be theta sub L on that. We'll use theta as theta sub L, and we'll get the small one, I guess, initially. We'll figure out where we're at. We'll know what's small, we'll know what's big. It should be pretty obvious. Well, I'll tell you what I tried to do last time, and like I said, I got caught up with the trigonometry a little bit. I can't keep getting caught up with some of the mathematics. The mathematics, at some point, we got to have well under control. But early on, I think it was good that I got caught up with it a little bit. So it's there for you. Look at it. There's some great tutors, and we'll just figure this out as best we can to our ability here, to the best of our ability. We have this, and I'm trying to figure out something. Well, I'm trying to get the theta that's going to work, and I'm probably going to get a real small angle of theta, and the other one's just going to be 90 degrees. It's going to be its complement. So we'll see. Let me kind of talk about what that is. Let me do it, and then Tell me how you guys feel about it. I mean, when we meet again and stuff, we can talk a little bit more about it. Tell you what I'm going to do. Let me multiply by g on each side, and let me divide by v squared on each side. Some people have already seen me do this verbatim already, and then I got, like I said, I looked at some other stuff I thought needed to get looked at, and I still thought needed to get looked at. Let me multiply by g on each side and divide by v squared on each side. So we got this. Sine 2 theta equals gx over v squared. Stay in non-numeric symbolism as much as you can. That's your business. If you don't want to do that, you get it right, you should be okay. You get it right, you should be okay. I'm looking at this. How do I get the theta by itself? Why don't you get the 2 theta by itself? Didn't we deliver a speech? The way you kind of get this argument to kind of be by itself is go inverse sine onto the sine function. If you do something on one side of an equation, you absolutely must do the same thing on the other side of the equation. The inverse sine of sine 2 theta is 2 theta. The inverse sine of gx, and we've done some of this in the class before, so we should be all right. At least with some people. You get to here. 2 theta equals the inverse sine of the ratio of 2 theta equals the inverse sine of the ratio of the product. 9.8 times 5,000. 5,000 is the range. Divided by v squared. V is 1,000. You square it, you got 1,000,000. Right, and we got, like I said, we got a little bit of a surprising result. We'll do something different, and you'll see that this is a little more of a common sense look to it if I change the numbers a little bit. But let's stay with where we got. I am looking at this. This should be, there's a lot you can go here. If this was a 10, this would be 50,000. Well, it'd be 50,000 minus 1/5 of this, which is 49,000. Or is it? Let me see here. 1/5. Yeah, sure looks like it, guys. Let me kind of look at. Yeah, I think it's 49,000. So it's 49,000 if you do the multiplication over 2 theta equals the inverse sine of a very small number, probably indicative of a very small angle. 49,000 divided by 1,000,000 is 49 over 1,000 is 0.049. You get the inverse sine of that, we got 2 theta. And make sure your calculator is not in radians, unless they're asking you for radians. We are responsible for knowing where the calculator is set. Typically, we're dealing with degrees, unless told otherwise, but not always. I mean, they might be making the assumption of radians. If they're using radians in other problems, it's your responsibility to be aware of what they're using. They should make it very clear what they're using within the context of the problem. So what we have here, like I said, every calculator is different, guys. Say inverse sine 0.049. Let's try that again. $2.808617. Okay, we're not going to make a huge deal out of this, guys. The big thing is I just want you to know what's going on. 2.81 ain't a bad way to go. A lot of times within the context of what you're doing, as I said, take it as far out as you can. In this instance, I'm not going to just to emphasize what's going on. But within the context of a problem, 2.8, 2.808617877. Yeah, there are times you should actually do that. Many times you should be doing that. For right now, we're not going to make a huge deal out of it. Let's make it 2.8086. Let's make it 2.81. Don't even have to go there. But, I mean, at least with the context of what I'm trying to say here, guys. But this is 2.8. I mean, it's whatever. It's kind of regretting going that far with it, but let me go with it. 2.808, I'll say 2.81 degrees. If you divide it by 2, that's going to be 1.405. Man, that is not a big angle. Theta is 1.405. Here it is. 1.405. 1.405 degrees. Now I'm going to talk about this a little bit more. That's the low one. What are you talking about? What we're talking about is that cannon is barely projected above the ground. That cannon is barely lifted up above the ground. But it is lifted up. Just don't go near it. Obviously, look at the angle it's taking. But that angle will give you 5,000 meters of range exactly. It'll land 5,000 meters away if the angle theta is 1.405 degrees. Wow, okay. Let's see. Now that's theta sub L. And I told you guys there was a bit of a trick in this thing. In fact, not only did I tell you there's a bit of a trick, I showed you the bit of the trick. If you take theta L and subtract it from 90, you get theta H. And I'm gonna explain why that's true, actually. Right now, let's just do it. Let's just get this thing right. So you're looking at this, and what's 1.405? What's 1.405 subtracted from 90? It's 88.595. Wow, this thing's almost straight up and down. If it's straight up and down, it ain't going to land anywhere near 5,000 meters away. But if you angle it just a little bit, close to being straight up and down, this thing will go up, and I mean it'll go up forever. We need it to go up forever because we need go up forever and come down is a big flight time. We need the big flight time because this angle gives you a huge vertical velocity but a very small horizontal velocity. You don't have a great speed. You better have a lot of time. So let's project it upward. Let's project it upward almost straight up, but not straight up. And there you go. You got these two things here. Now, that's what I said. Now, where did that kind of come from? Something on this board. Somebody wrote on this. So they weren't able to erase it, so I'll write right over it. How's that? Here's a sine wave for you. This is 90 degrees right in the middle. This is 180 degrees, or pi radians. This is 0 degrees, or 0 radians. This is pi over 2 radians. This is perfectly symmetric. If you go over on the low side, and let me make this kind of big so we can see it. If you go over this way, 1.405 degrees over this way. You go over this way, there, you're up here. Why don't you go all the way across? All the way across is also 1.405 degrees. 1.405 degrees, and I didn't draw this too good, but 1.405 degrees away from this guy. It's 180 minus 1.405. Yeah, well, Jim, that's not 88.595. No, but it's 177. Let me think here. It's 177.19, something along those lines. And if you subtract it from here, you got, forgive me, no, that's wrong actually. If you take this will be 170. Just trying to figure out what I did here, guys. I want to make sure this is on the right side here. Yeah, I guess it is. For some reason here, I'm getting an answer that is something I don't want to get. Let me see, 8, 9. No, it looks like it's okay. Kind of doing this, guys, completely on the fly. So let's just make sure we're okay. I think we are okay. Should be okay. So if you do the subtraction here, you'll get 178. Forgive me. Yeah, let me see here. You'll get 178.595. Let me think here. No. Okay. No, here. Okay. I'm sorry. Here's what I did wrong. Forgive me, guys. Yeah. Let me not do that. Let's come back. I'm sorry about that. That's all right. We got it. This is 2 theta. This guy right here is the other 2 theta. This is 2 theta high. This is 2 theta L. This guy right here is the 2 theta is 2.8. 2.81 degrees. Now, here, this is to the right, starting at 0 right here. This is to the right, 2.8 for the 2 thetas. This is to the right, 2.81 degrees, and this is also 2.81 degrees, but to the left. What does that mean? Well, that means 180 minus 2.81, which is 177.19. Okay, I said that earlier, but didn't really bring it together. 2 theta h is 177.19. Well, I don't want an angle like that. And this guy right here is 2.81. Well, if you divide by 2 on each side, you got the 1.405 for theta L. You got the 1.405 for that one. And if you divide by 2 here, you've got, well, yeah, let me look at it. Let's make sure we got it good. It's looking pretty good. Yeah, it's going to be if you divide this by 2, indeed, you're going to get the 88.5. Theta sub h is the 88.595. The reason that works is this is 2 theta right here, and this is basically the same 2 theta distance. 2 theta going to the right is 2.81. 2 theta to the right of 0. 2 theta to the right of 0 is 2.81. 2 theta to the left of 180 is 180 minus 2.81, which is 177.19. Yeah, and then that's what 2 theta equals this mess, and 2 theta equals that mess. 2 theta low is the small guy, 2 theta h is the big guy, and that's what we got. There is a shortcut on this. What happens is these 2 guys, the 177.19 degrees and the 2.81 degrees, add up to 180. What does that mean? That means that 2 theta L, the doubles now. The 2 theta L, the 2.81, and the 2 theta h, the 177.19, when you add them together, you know, the 2 theta h is this, the 2 theta L is this. When you add them together, you get 180. Let's just say that. That's generally going to be the way it is. It's equal to 180. That's equal to 180. Really? Yeah. Tell you what I'm going to do. What do you say you divide both sides by 2? You can factor a 2 out of here, guys. And you got 2 theta L plus theta H over 2 equals 180 divided by 2 is 90. Well, guys, you run out of room at some point here, but don't like erasing any of this. I always forget, though, that we always got the option to go back. We always got the option to speed up, and we always have the option to speed up. We always got the option to go back as well. So, at the end of the day, we said 2 theta L plus 2 theta H, they all equal 180. You saw the 2.81 plus the 2.81 plus the 177.19, they add up to 180. 177.19 and 2.81, okay. They add up to 180. If you divide by 2 on each side, let me just give it a little more room, guys, in case you didn't follow me. Divide by 2 on each side. $180 over 2 is 90. They cancel, and this is what I was saying earlier. Theta L and theta H are complementary angles. That means they add up to 90 degrees. If you ended up finding that this guy was 1.405, this guy right here is 88. You know, if you found out that the other one was, if you found the other one was 1.405, the other one is 88.595. Simple as that. I mean, if this is 1.05, what would you add on to 1.05 to get theta H? Why don't you just subtract 1.05 on each side? When you do that, you get theta H to be the 88.59, the 88.595 degrees. So this makes it a lot easier. I didn't get a chance to talk about that today. I mean, and like I said, a lot of you, I'm not sure who's watching, guys, at this point. Hopefully a lot of people watch. Those who don't have me as a teacher wouldn't have seen anything of what I did. Hopefully you're seeing this and it's making some sense. It's about as simple as that, you guys. It's about as simple as that. Let me erase a lot because there's a lot up here. So, you know, you remember it's 1 kilometer per second. That's 100 meters per second. It's 5 kilometers. That's 5,000 meters. So x is 5,000 meters, and v is 1,000 meters per second. Okay, so these two add up to 90. It's a good way out. So let's see. We know the horizontal projection of velocity. Notice the velocity, it doesn't matter what angle I use, I'm going to get there. There's a question of how I'm going to get there. I may want to hire it really far up into the air so I have time to get away, if I'm military personnel or something like that. I may want to fire it very high up in the air and it gives me a chance to get away. They're all going to cover the same distance at the end, exactly cover the same distance at the end, while they're looking to try to hit a particular target for, you know, some sort of exercises or whatever's going on. So if that's the case, you just know that there really isn't a lot of horizontal projection, but you got a lot of time because it's being fired straight up. There's a lot of vertical velocity, not a lot of horizontal velocity. Here, there's a lot of horizontal velocity, but not a lot of vertical velocity. But you know what? The speed coming out of the cannon is the same for both scenarios, 1,000 meters per second. 1,000 meters per second. I'm sorry, just 1,000 meters per second. Let's see. I should have brought my other eraser as well. I like to use 2 erasers sometimes. It's what it is. I mean, circumstances are what they are sometimes. So we got what we got. We're here. Let's take this. We know that everything is here. It's a click away from going backwards and looking at the diagrams and looking at the equations and everything else. Well, let's look at theta sub L for that purpose. What's going on with the theta sub L? I mean, so the time the time of flight associated with the low angle, the time of flight is going to be given by 2v sine theta over g. Man, it just can't be a big number because the angle ain't big. You got 2, you've got, 2 is 2, v is 2, v is 1,000. The sine of 1.405 degrees is this. Depending on what class you're in, they'll use, in some of the classes, I think the CATS book uses 9.81. Serway book is going to use 9.8. Let me stay with the 9.8. Generally, just kind of use what the language is that they're trying to use, guys, when you're doing some of this stuff, okay? That's about it. So there's a number of ways you can go. Let's just do the numbers here, guys. You grind out the numbers and you should be okay. So we'll see how we can write it. Some other numbers that can be put in here. Okay, so I just erased something I didn't want to erase in my own calculator here, but that's all right. 2 times 1,000. 2 times 1,000 times the sine of 1.405. Got to make sure it's degrees. Make sure it's degrees, guys, okay? Okay, we got that. That makes sense, about 49.03, okay. Right about there in the ballpark. Divide by 9.8. 5.0039. 5.00396. 5.004. For our purposes right now, guys, that thing's going to fly for 5 seconds. I got to make, right now, my big thing for you is to make sure that you're okay. I mean, it's working out here. What's the height? Height's an interesting matter in its own right. The height, h sub L, or any kind of height for that matter, v squared sine squared theta sub L, right? It should have been a theta sub L here. Whatever theta is under consideration. For the high, you're going to put an h. You've got this. And let me try to look at it, guys. Let me try to put 2 and 2 together on this thing. 2 times g. Yeah, sounds good to me. Man, this thing can't be going that high. At its apex, it ain't. I just don't see it going real high, but let's see where it does go. I mean, let's see where it goes. V squared is 1,000 squared. Sine squared theta L is sine squared 1.405. 2 times g is 2 times 2 times 9.8 is 19.6. Let's go. See what we can say here. There's a number of ways to go here. Let's do something. sine 1.405 times sine 1.405. Wow, at its apex, it's not going that high. I mean, it's that 5-second journey, it's 30.67. 30.6735, that's the height. Where would you have to walk on the journey to look up and see that the thing is 30 meters above you? Man, I really want it to be 30 meters above me, no closer than that. Maybe it's a good idea not to walk anywhere. That's still pretty close. It's above you 30 meters. It's about 100 feet above you, right? At its apex. Well, the whole journey, you guys, is a 5-kilometer distance. Half of 5 kilometers. Half of 5 kilometers is 2.5 kilometers. 2,500 meters is the halfway distance. From 0 meters to 5,000 meters, the halfway distance is 2,500 meters. At that point, if I look up, the thing will pass like this. Let me just double check it, guys. I mean, what's so frustrating about these is you make it. Let me just try to. Just don't want to make a careless mistake. It looks pretty good. Looks pretty good, guys. 30.67 meters. Not too high, man. You're going to go 2.5 kilometers to see this thing reach its maximum height. And man, that ain't too high, but there it is. It is the exact same argument. My friends, it is the exact same argument when you're going to proceed over here. You're going to use, there's a lot you're going to say. I mean, you could say, okay, let me go here. Again, I wish I had my other erasers, guys. There are other erasers. I like the ones with the cloth. But let's see what we got here, guys. We got this. Got this. This is going to be something different. T sub h. Yeah, that thing gets fired up almost at a 90-degree angle. Not quite, but if it does, you know the flight time is going to be more than 5 seconds. It's the same argument, guys. It's everything we've done up to this point. Just be careful. Just kind of see where everything is. T sub h, you can just generically leave it as is and just, leave it as t and just put the appropriate angles in there. But it's the same dynamic. It's the same mathematics that's been taking place, you guys. Just watch out. V is the same. Sine theta h, 88.59. 595 degrees. That's that. This is 88.595 degrees. Let's go. Let's just here you go. Just plug it in. It's the same exact argument. Let's see how this whole thing proceeds. You're going to say, go carefully here. Sine of 88, and make sure you're responsible for knowing that your calculator is functional in this regard. Now I'm going to check it as well. I mean, maybe you should have checked it earlier, but at some point before I'm giving a final answer, let's check this stuff. Make sure we got this thing the right way. The sine of 88.59 times, okay, let's kind of see, right. Right, and then multiply that by 2 times 1,000, multiply by 1,000, 2 times 1,000 rather, which is 2,000. This divided by 9.8. 204.02 seconds. From 5 seconds to 204.02 seconds. Yeah, that's a long flight time. That gives me a lot of time to get away. 3 minutes would be 3 times 60, 180. This is 3 1/3 minutes. A little more than 3 1/3 minutes to kind of get out of there. You know, if you have a vehicle and stuff in the military exercise that's being done here. So this is what it's looking like here. Same argument, guys. Same argument. It's the same argument, but you have to be exceedingly careful when you do this stuff. When you do all of this stuff, there is the idea of precision. The sine of 88.595. The sine of 88.595 squared. The sine of 88.595 squared is going to be equal to that times 1,000 squared, which is 1,000 times 1,000, which is 1,000,000, divided by 19 point. Man, you're not kidding, man. This really took off. About somewhere in the ballpark of 50,990. Now, I'm rounding off. Generally don't do that when you're taking an exam. Be more precise. Be more precise. I'm telling you, this is crazy. That thing's going to go about 51 kilometers into the air. I mean, that is something else. You know, it's like 32 miles in the air. Man, you do got, I mean, again, assuming no air resistance, that is something else. So 50.99, you know, so we got here. Let me see. So we got 204 seconds and 50,990. And that's probably too much of a round off, guys, but I'm trying to give you a ballpark idea of what's going on. First of all, let's see if it's right. I mean, that's you know, this could easily go wrong for us too. Double check it. 88.595, get the sine. Then multiply it again by the sine of 88.595. Just be real rigorous about it if you want. Multiply that by 1,000 squared. Divide it by 19.6. Getting a little different answer here, but not far off. I have no idea why it would do that. Maybe it's just the way the round off goes. I'm getting 51,005. Yeah, that is a little odd. Let me see what I can do. I mean, 51,000. Look, it's in the ballpark of 51,000. For right now, that's okay. I just want to know. Sine of, I might have put in the wrong numbers. I mean, that's true too. I mean, they're all in the ballpark. That's not a big deal. I divided by a number that was too big. I might have divided by 19.8. That could be. Now I'm getting a different answer. This is very odd. I think it's the way. I think it's the way the round off is taking place, you guys. For our purposes right now, this is good enough. Something's going on with the algorithm in the calculator, but you know, the 51,000 is a pretty good ballpark. You know, if you want to round it, I don't know, I'm kind of tempted to round it a little bit more and make it 51,000. This isn't really the big deal right now, guys. The big thing is, I mean, later on, precision is going to be real important. And wow, exactly doing this thing right, we're getting different answers every time we're doing it. Very, very strange. Again, I'm going to have to just, I got to look at that again. That's just very, very odd. 88.595 times the sine of 88.595, guys. Yeah, I'm getting 50,989.73. So I'm getting. I'm going to stay here. I'm going to stay here. It's somewhere, you know, it pays the check. I had to check about like what 5 times, but it seems to be coming right back to here. So this is where we're going to stay with this. Anyway, that's what you're looking at, guys. That's how you're looking at it. Doesn't matter what you're putting in there. I mean, if this would have been a whole lot easier number to deal with if somebody would have said to you, hey, you know, by the way, V is 500 meters. V is 500 meters per second. X is 5,000 meters. Is this all going to be more believable when we're playing this game? Yeah, absolutely. I mean, if they, now that's, you're done. I mean, that's it, fine. You know, for V equals 1,000 meters per second and X equals 5,000 meters. End of the story. That's that. What if somebody changed it and did something like this? Yeah, I mean, they're basically doing the same thing all over again. You'd have to, now if they threw this, it's just for the heck of it. But the way we're resolving vectors, guys, the way we're resolving forces, you're finding the x component of a vector, you're finding the y component of a vector, you're finding the magnitude of a vector. All of that cannot be done without a decent knowledge of basic algebra and basic trigonometry. So you have to have that under control, okay? You know, where's this going? Well, it's going where the other one went. It's kind of the same thing here. Let me, you know, how much time do we got on it? You know, we could say theta sub L for this guy, and that's for this one. That'd be theta sub L, T sub L, H sub L, theta sub H, T sub H, H sub H. If it looks familiar, it's very familiar. You can do the exact same mathematics to knock this thing out. You're going to look at it, you're going to kick it around, you'll say, okay, well, look out. This is a big difference. I mean, now we're saying, you know, we set it for these guys, and we're done. Now we're doing it for these guys. Totally different. You all know V squared over L is this. Here we go again. Do the exact same algebra I did earlier, guys. Multiply by g on each side and divide by v squared. Get the inverse sine on each side. You get the inverse sine on one side, you do the exact same thing there. Even if you make up a function, whatever made up function it is, you better do the exact same thing on each side of the equation for it to remain an equation. You get 2 theta here. Well, let's treat theta to be the L guy, the low one. 2 theta equals the inverse sine of 9.8 times 5,000. Well, a lot of stuff sure looks familiar. Yeah, it does. Yeah, it sure does, but the V is different. The V is different, you guys. The V here is no longer, it's no longer 1,000. It's 500. Here goes. Should go smooth. Should go a lot faster than we did the other one. Let's just be careful. You saw how this can happen. We got the right answers, at least to the best of our ability we did, right? And so let's go. You're going to get the inverse sine. You plug in all the numbers, grind them out, you guys. So inverse sine of this thing right here, as we said, was 49,000. This thing right here is 250,000. It's a little more believable of an angle. Not that the other one's not believable. It's believable, but man, it's kind of a rather spectacular result. If you're going to give it that kind of speed, how are you going to make this thing work? 303 or just 3? Just put it's 303, but it's this. Theta is half of that, which is 5.65. All right, still, that ain't much of an angle, man. I'll be honest with you. Maybe I need to fire this thing further away. If I was firing this thing not 5 kilometers away, but let's say 50 kilometers away, you'd have to increase the angle to increase the flight time for both of those. Both for, well, you can argue that one. Some interesting things happen. But the bottom line is they got to add up to, they have to add up to 90. So this is this guy. And theta sub h is the complement of this. The complement is what number added to 5.65 degrees. What number added to 5.65 degrees is going to give you 90. What number added to 5.65 degrees is going to give you 90? Looks like 84.35. That's still kind of a crazy, just when I thought make this thing a little more sane to look at. Well, it's still okay. I mean, it worked. But you can see it's still some pretty crazy stuff going on with this. So this is basically the argument, you guys. You're saying 5.65. And the other guy is 84.35. The flight times are going to be different. I mean, flight times are going to obviously be different. So you look at situations where the T sub L is going to be V squared sine squared theta L over, forgive me, And the other one is going to be T sub H is 2v squared sine squared theta H, sine squared theta H, whole thing over G as well. Yeah, I mean, it's a bit of a mess, but let's see. The low one's not going to have a big flight time. It's going to be more than 5 seconds. I guess that's some consolation to the whole thing, I guess you could say. You take the 5.65 and put it here, and you know, and that's it. I mean, just trying to figure, just trying to say something, you guys here. For some reason, I did not. No, I don't think it was. I don't think I have to square those. Let me. Let me just double check this before we leave. I mean, from where we are. T sub L is 2v sine theta over G. T sub H is 2v sine theta. Here's the H, here's the L, here's the G. I hope I didn't, yeah, let's make sure we're on the mark here, guys, when we're doing this stuff. Yeah, I think it's fine. I think it was fine. Let me just quickly check the times on this. I think the times are not a problem, but let's just double check it from before. I'm saying 5 seconds. That sounds about right, man. Or does it? That's just it. For the 1,000, let me just see here, guys. We'll do 1,000 times the sine 0.405 times 2. Yeah, it sounds good to me, guys. Divided by 9 point, okay, multiplied by 2, divided by 9.8. Yeah, no problem. That's correct. We did it right. I just don't have the feature right now, guys, to look back at something the way it is. So it was right. It's right because this is kind of the argument. This is the argument. There's nobody being squared here, and we were actually able to do this. You're going 2v sine theta. You're going 2v sine theta over G, and that's what we did here, and that was fine. You did sine. Let's just to double check it, guys. Forgive me. 1.05. Let me just try here. 2 times. Right on. Yeah, it's right on the mark. The other one would be same argument. I'm sure it's fine, guys. Like I said, I don't have the feature. Just look back and double check a little bit, but let me just do it anyway. Yeah, it's right on the mark, guys. Everything's fine. Yeah, so that's how we were doing it. This is what we did earlier. There's nothing being squared here, but when you're finding the height, there's going to be that square component to talk about. There's something squared here, obviously, when we're finding out what theta was, and then down the road, you're going to have h associated with v squared, and that's what we did last time. That was fine. That right there divided by 2g. And we did all kinds of stuff with that. I mean, yeah, something else, guys. I mean, we had, just do it one other way here to kind of get an idea of what we're doing here. Yeah, right. It's right on the mark, guys. Just to double check it, guys. The last thing I want to do is put this stuff out there and just lead you astray on it. Let me look at the other one, which is yeah, the 50,989. It's showing up all over the place, guys. The other one was a bit of a fluke. Somewhere I'd made a mistake on it, but this is fine. Everything's on the mark as we're doing this. We got this. Might as well leave this up here just to kind of protect ourselves, I guess you could say, when we're doing this thing. We got this. Let's see where this is going. I mean, should be of interest. I mean, how does this play out? We'll plug in the numbers here. This will be theta sub L. That's 5.65 degrees. This will be theta sub L is 5.65 degrees. Theta sub H is 84.35 degrees, and just do the work we got to do. Let's go. The way I would look at it is, just plug in and go, guys. 2V sine theta L. Theta L is 5.65. Sine of 5.65. Yeah, absolutely. Divided by 9.8. 20.09 or 20.09, 20.1. Well, that's more than the low guy had earlier. The low one was almost at ground level. You had 5 seconds of flight time way over here, you guys. 5 seconds of flight time when the angle was 1.405. Here so you had 5 seconds of flight time for the angle 1.405. Here you got 20.1 seconds of flight time when the angle is bigger than 1.405, by a factor of 3.5 or so. I mean, the 1.405 angle got you 5 seconds of flight time. The 5.65 degree angle got you 20.1 seconds of flight time. And you're just playing the same game here, guys. You're saying you're plugging in the appropriate numbers. You got to be careful. I mean, like I said, we makes you question what you're doing sometimes with this. So I'm going 2 times 1,000 times the sine of theta. Theta here is 84.35. Sounds good to me. Divided by 9.8. Yeah, this ain't a joke. I mean, this is 203.1. Yeah, I mean, you ain't changing it a whole lot. I got 204. It's not quite the flight time, but it's quite the flight time regarding some of this stuff, you guys. So that's what it is. Yeah, rather interesting. I mean, it's just to double check it. I mean, 2 times 1,000 times the sine of 84.35. You got it. It's this. So, I mean, I guess that we would see more of a difference if we were with those kind of velocities coming out of the muzzle there, guys. Maybe we'd have to go. Maybe we could hit from a lot further distances, not 5 kilometers away, maybe 20 kilometers away, not 5,000 meters away, not 5,000 meters away, but 20,000 meters away, maybe 100 kilometers away. Maybe 20 times that distance. We'd have to look at it. We see what the capabilities are on the process here. But again, it's all in the numbers, you guys, when you're doing this thing. Well, I mean, the heights are going to be big. I mean, when you look at this whole thing, 20.1 and 203.1. HL, well, here we go. This one's going to be definitely higher than the 30.67 meters. Let's see what's in there. Let's see what we got. You've got you got the 1,000. You've got the 1,000. You've got the sine of 5.65. The 1,000 is okay, get an answer. Okay, let me just try that again. The 1,000 times the sine of 5.65 okay. I think it's fine. Divided by 2G, which is divided by 19.6, 494.524. Wow, kind of just a real surprising conclusion, I guess you could say. But it is what it is. I mean, it's certainly not at 30. That's odd. It is and it isn't. I mean, because this sure ain't a big angle, but it's an angle that is opening up, about. I'll tell you, it's opening up at an aperture of 4 times more than what was going on earlier. Yeah, no, still that doesn't, but let's check it. I mean, let's check it again. We got 1,000 times the sine of 5.65. Yeah, it's quite a bit. The other one is really close. It's going to have to be really close to what the other one was. Let's take a look at it. We got this times the sine of 84.35. Pretty big number. Yeah, I mean, 50,526, about. Yeah, that's surprising. This is not surprising. This one kind of is, but it's what it is. I mean, it's you figure for small angles, if it's 4 times more, the opposite side in the ratio is if the angles are close to, I don't want to get too far into this. It'd be easier with radians, actually, but this is about 4 times. This is 4 times bigger opening, 4 times bigger raising, 4 times bigger raising than the 1.405. The 1.405 goes into here about 4 times, literally. The leg opposite this angle is 4 times bigger. If you multiply by 4 times bigger, but square it, it's 16 times bigger. 16 times 30.67, that does hit you in the ballpark of 480, 490. It is believable. The other one's kind of odd how it worked out, but it works out as it works out, guys. Anyway, this is the basic argument. Know what's going on with this stuff, guys. Know what's going on. There's a lot can be said here. A lot can be said. It really is. I mean, what you could do, I mean, just for argument's sake, you could say, wait a minute, is there a way I could kind of just do some mental gymnastics here and just get the same answers for H sub L and H sub H, H sub L and H sub H? Tell you what I'm going to do. H is this guy. I maybe got a different way to show you. V sine theta is the initial shoot-up velocity for Vy. The initial Vy component is V sine theta. The final Vy component at the very top is 0. Why don't you take, you don't have to do this. I'm just saying, let's, for the sake of just discussing some of this stuff, guys, get a ballpark idea where the numbers are. You guys remember what I've said for the kinematics. You guys remember what I've said for the kinematics, you guys, that we're talking about didn't we say like the distance traveled, or let's call the distance traveled h. Isn't there an initial velocity of v sine theta when it's first shooting up? That's the y component initial being shot up. And at the very top, the y component is 0. Why don't you take this, divide it by 2, and then multiply it by half of the total, multiply it by half of the total time. The total time of flight is from here all the way down to here. I just want half of that right here. I wonder if the low one, for example, for this guy, 5.65, why don't you take 1,000? Why don't you multiply by the sine of 5.65, add 0 to it, which is just the same as you got, divide by 2, and multiply it by half the flight time for this guy. For this guy, the new one, the 5.65. The 5.65's got a 20.1 flight time. 20.1 flight time divided by 2. Hey, we've made the claim, right? We could do averages. As long as it's a constant acceleration, this constant acceleration's got a special name. In this case, it's called a deceleration. It starts out fast, and you bring it all the way down in a uniform manner. Man, H sub L, man, I hope I get at least in the ballpark of 494.52. Here goes. 1,000 times the sine of 5.65. Get an answer. Divide the answer by 2. Get an answer. Multiply by 20.1. get an answer. Divide by 2. 494.718. $494.718. That's pretty damn close. That's 0.19 off. That's way, way less than a 1% error. That's like 1/20th of a percent error. If you took this, let me show you, just kind of get a ballpark idea. Yeah, it's it's 3.84 times 10 to the negative 4. In terms of percent, that's 3.84 times 10 to the negative 4. That's 3.84 times 10 to the negative 6. 3.84 times 10 to the negative 6% error. Good enough. So in that ballpark, guys. So, I mean, we looked at it. Unfortunately, I almost rewrote. Okay, I almost went right past this thing. 494.72. So on and so forth. How did we do it? We went here and we remembered that D was VI plus VF over 2 times some kind of a T. That is not visible too well, guys. Let me try to make this. We just used the game D equals VI plus VF over 2 times some kind of T. D was the V sine theta, some theta, right? Theta happened to be 5.65. This guy's 0 divided by 2. This small t was the big T divided by 2. We did the song and dance, make the D and H. It's a distance going upward. It's the same thing. The more athletic you are with these manipulations, the less chance there is that you're going to make a mistake. You can always check yourself as to what it is that you're doing. Obviously, you don't want to get too, there's a time and place to do all this stuff. The bottom line is when you're taking an exam, get everything right, do what it is that you know how to do, and then you can look at some of the subtleties of it. But there's so many different ways we can do this. Those of you who have had me in a particular class that was non-calculus based, remember how we did that problem where an object was fired straight up into the air, and we looked at a number of different ways that we can solve for the time that is involved. We can solve for the height that is involved. We could even find out how fast this thing is going at the end of it if you're using the kinematic equations that we've seen in the past. Okay? Sounds pretty good. Everybody do well, and take care.